Let us now look to the proof of the algorithm and prove that the algorithm achieves linearizability for multiple writers, multiple readers with multiple registers. So let's remember some facts about linearizability. Linearizability of a trace T or an execution T requires that there exists a legal history, and this legal history is a sequential history where each read reads the last value written, and this history should be equivalent to the real-time trace. And if operation O1 precedes operation O2 in the real-time trace, it must also precede O2 in the sequential trace. And remember, linearizability is compositional, so if the trace restricted to a single register is linearizable, then the trace is also linearizable for all registers. So we are going to focus on an arbitrary register XR and prove that the trace restricted to a single register is linearizable. So what we are going to do now is, by construction, construct a legal sequential trace and then prove that it is actually linearizable. So let us see how to do that. We first say the following, that the timestamp of an operation O, which we call it TS of O, is a timestamp used in O's update phase. So it is a timestamp if we have a write operation, the timestamp the write operation used in the update phase, and it's also the timestamp that the read operation used to do an impose. Now let us construct a sequential trace from the real-time trace restricted to register XR as follows. It is in timestamp order. So how we do it? We order write operation according to their unique timestamp, the timestamp TS and PI, the process identifier, and then we order each read operation OR immediately after the write operation with the same timestamp. So this is the timestamp that the read operation has read. Now we can get multiple reads with the same timestamp. So what we do, how to order the multiple reads? We order them in increasing invocation order, the invocation of the operation in the real-time trace. So this trace is sequential, and it is also each read operation reads the last value written. So this trace is legal by construction. So now the trace we have sequential, and read returns the last value written. So what should we do now? We must show that for each execution and for each register R, we can achieve linearizability restricted to that register. And this requires two things. First, it requires that there exists a legal history, S, and we have that already. Our legal history we just did by construction, which is sequential. And also requires that S is equivalent to TS. And equivalent means each process in the sequential trace has the same view as in the real-time trace. And S preserve order of non-overlapping operation in the real-time trace restricted to register XR. So we are going to look later to this condition, which is S preserves non-overlapping order as the real-time trace. Given that we have that, we conclude that S and the real-time trace are equivalent. Why? Because they contain the same events, and because each process is sequential, each trace here contains non-overlapping operations, and because S preserves non-overlapping operations, then these two traces, S and T, are equivalent. Hence, T restricted to XR is linearizable for register XR, which implies by compositionality it is linearizable for all registers. Now we are left with proving that S preserves non-overlapping operation as T. So here we are now. We must show that S preserves the order of non-overlapping operations. So let us call T restricted to XR as T prime. And what we want to prove is the following. For any two operations O1 and O2, if O1 precedes O2 in the real-time trace, then it must also precede O2 in the sequential trace. And this, remember what it means? It means if the response of O1 precedes the invocation of O2 in the real-time trace, then the response of O1 precedes the invocation of O2 in the sequential trace. Or just it's enough to say that O1 precedes O2 in the sequential trace. So now we have to do some case analysis depending on what kind of operations are O1 and O2. So assume O1 and O2 are right operations, and we can see it here. Here is the operation O1, and here is the operation O2, and each one consists of a query phase and update phase. And here is the response of O1, and here is the invocation of O2, and we know that the response of O1 is before the invocation of O2. So what we want to prove now is if O1 is before O2 in the real-time trace, then it is also before O2 in the sequential trace. Again, it means the response of O1 or O right 1, so I will say O1. It's understood that these two operations are right operation. The response of O1 is before the invocation of O2. Then we want to prove that the timestamp associated with O1 is less than the timestamp associated with O2, because that is the way we order operations in the sequential trace. As we can see even in this picture, the update phase of O1, as you can see here, is before the query phase of O2. When O2 performs a query phase, the query returns a timestamp, and this timestamp is guaranteed to be greater or equal the timestamp of the right operation O1. It can be equal to the timestamp of O1 if O2 immediately follows O1 with no intervening writes, or it is greater if there are some intervening writes. In both cases, O2 increments its timestamp, and therefore the timestamp of the right operation O1 is always less than the timestamp of the right operation O2. And by construction, this means that the right operation O1 is before O2 in the sequential trace. So second, assume O1 is a write and O2 is a read. We want to prove that if the write precedes the read in the real-time trace, then the write will precede the read in the sequential trace. And by this we mean that the timestamp of this read should be either equal to the timestamp of the write or greater. So let us see how we do the proof. So the response of the write is before the invocation of the read in the real-time trace, which would mean that the query phase of the read is after the update phase of the write, and that tells us that the timestamp of the write is less or equal to the timestamp of the read operation. So here what we said, the write update phase is before the query phase, so the read will return a timestamp that is greater or equal a timestamp of the write operation. It will be equal if it reads from that write. It will be greater if there are some intervening writes. And therefore, the write precedes the read in the sequential trace. Now let us see the case where our read operation is before the write operation. So we have a case where the read operation is before the write operation in the real trace, and we want to prove that it is also so in the sequential trace. Again, it means that we have the response of the read operation in the real trace is before the invocation of the write operation in the real trace, and this means that we want to prove that the timestamp of the read operation is less than the timestamp of the write operation. So here's our case. The result of this read is before that write, and we want to prove then that the timestamp of the read is less than the timestamp of that write. So the timestamp of the write operation here, OW. So our read operation update phase, this one, is before the query phase of the write. So the query phase of the write return a timestamp that is either equal or greater than the timestamp of the read operation. In both cases, the write operation increments the timestamp. So the timestamp of the write operation is strictly higher than the timestamp of the read operation, which actually means that the read operation in the sequential trace comes before the write operation in the sequential trace. Now let us look to the last case where we have two read operations. And we want to prove that if one read operation is before the other read operation, so read operation R1 is before read operation R2 in the real-time trace, it is also true in the sequential trace. So, which would mean we want to prove if the response of the first read operation is before the invocation of the second read operation, then the first read operation is ordered before the second read operation in the sequential trace. This can happen in two cases. Either the timestamp of the first read operation is less than the timestamp of the second read operation, or the timestamp of the first read operation is equal to the timestamp of the second read operation, but the invocation of the first read operation is before the invocation of the second read operation in the real-time trace. So we know that the update phase of the first read operation is before the query phase of the second read operation. We know also that the query phase of the second read operation is going to return a timestamp that is greater or equal the timestamp of the first read operation. This is because if there is no intervening writes, it will return the same timestamp, but if there is some write in between here, then it will return a higher timestamp. So we have two cases. The first case, if the second read operation returns timestamp higher than the first read operation. In this case, in the sequential trace, we know that operation OR2 is after operation OR1. There is at least one write operation in between. But if we have the case where if they have the same timestamp, then we order these two operations by invocation order. So it means that operation OR1 should come before operation OR2. Therefore, we know that invocation of R1 is before the response of R1, which is before the invocation of R2. Therefore, the invocation of R1 is before the invocation of R2, which means that they are ordered in that order. Therefore, read operation R1 is ordered before read operation R2. And that actually completes the proof of multiple writer, multiple reader that is linearizable.